class, welcome back to our lecture series, Miss Cose's Pregnancy Lecture Series. Today we're going to start a brand new unit on the senses, which are really fun. And actually we're hoping to keep these lectures a little bit shorter so that you guys can do an interactive activity with each of the senses. So today's sense is pain and touch. I think you guys are going to enjoy what we're going to do. But I want to first introduce you to our very special guest today. Probably one of your favorites. I know she's mine. Kelly Dahman! Give it up! Give it up! She's going to be our student today. And so I think you guys are probably excited about that. Let me make sure this is reset up. Okay. Nice. All right. So today we're going to be talking about one of our first senses, which is pain and touch. So to begin that discussion, I want to ask the class and Miss Dahman, Sub, you can pause it and get a response from anyone who wants to. But what is the most physically painful experience that you've been through in your life? I don't know if you guys know this, but Miss Dahman was like a legit stud track athlete, like Division I athlete. So I know she probably has some experiences. So Miss Dahman, what is like one of the most physically painful, and it may not even be from sports, but
yeah,
what do you think it is?
I have to say having a baby.
Okay, having a baby. Did you have a natural?
Before the epidural. No, I did get butt, and it took a long time till then. So it was like 20 hours.
Jeez.
Until I got the epidural.
Oh my gosh. Yeah. What made you wait so long?
They made me. I was not dilating. So they.
What?
Yeah.
So they made you just go
until I got to 2 centimeters, and I actually didn't. My water broke. But I was so thankful it did, because at that point they were like, okay, we got to keep it going.
Oh my gosh. Okay, that's saying a lot, because the other day at lunch, Miss Dahman told me about how one of her bursa sacs, which is like a lining of like joint, like fluid that is like a cushion. She's had one of those explode mid-race, and then she still got first place in the race, which is insane. Yeah. But it says a lot about childbirth. Oh, no.
Sorry.
I'm in for a treat.
Yeah.
All right.
It's worth it.
Well, that's good.
I did it 3 times.
So it's good to know. Yeah, so she repeated it.
Yeah.
I don't really know what the most painful, I don't know, what came to mind was just like certain run tests that we did. Like, even though they weren't like, oh, my leg's getting chopped off, it was like, ooh, this is like really hard and like painful in a certain way. And then I think probably just the students know that I like chopped my finger off one time. Like a lot of it off.
Wow.
Like this much. And it grew back like a starfish.
Wow.
But I'm excited for you guys to share and hear your experiences. But we bring this up because obviously we're talking about that today. But to kind of be more broad, our fifth sense, we usually think of our senses like sight, smell, hearing, taste, but then we get to touch. And touch is actually called somatosensation. Somato just is like the Greek root word for body, and sensation like to feel, touch, like sensory. So like body sensations. So when we think touch as one of our senses, oftentimes we don't incorporate temperature, pain, and even our body position, like being aware of our body in 3D space, but that all falls under this fifth sense, which is somatosensation. Now, I think I included a question here. Yeah, so this is for the students, because we just went over brain anatomy and what parts of our brain are in control of certain things. If you know this, you could answer it, but I know it's tricky. What is the primary lobe of somatosensation? I don't know if it is labeled here, but do you know any lobes of our brain, Miss Dahman? I know that's a long shot.
No, I don't remember.
Okay, so we have like our frontal lobe, which is in the front. That's like our processing.
Okay.
We have our occipital lobe in the back. It's vision. But we have a lobe on the side that's called parietal. It's on the top. And actually, in the middle of your brain here, you have a feature that's called the central sulcus. And it separates your frontal lobe, which is this section where we think and process, from the parietal lobe, which is here. And the students know that in front of the central sulcus is what? They're hopefully going to say our primary motor cortex is this whole section is our primary motor cortex. So our frontal lobe will help us determine like, oh, hey, I want to go grab these streamers and I made the decision to move, and so my primary motor cortex is there. But behind the central sulcus, where the parietal lobe is our primary somatosensory cortex. So any information that I'm receiving from moving and touching, feeling, texture is all coming to this part of the brain in the parietal lobe. So hopefully you guys got that. I think they did. They're really sharp. All right. So, parietal. Now, we have three main receptors that we're going to go through today, just the three in the somatosensation category. The first one is a mechanoreceptor, second is thermoreceptor, and the third is nociceptor. So, just by looking at the words, can you anticipate what each of these receptors might do? Or just one of them? What do you think?
Some kind of movement for the first.
Yes, something with movement for mechanoreceptor. What do you think about thermoreceptor?
Like temperature.
Yeah, like thermostat, exactly. So this is detecting temperature in our body. This one is not as obvious. Do you have any guesses? It's really hard. There's not a word root here.
Like night or day? No.
That's a good guess, like nocturnal.
Yeah.
Nociceptor refers to our pain receptors.
Oh, okay.
So we'll go through each of them right now. So starting with mechanoreceptors, like you said, it has to do with some type of mechanical movement, and you're right. It's detecting mechanical force and taking that force that we're feeling on our body, on our leg, somewhere inside of us, and then it's turning it into an electrical impulse, an electrical signal that can go up our spinal cord, up to our brain.
Okay.
So, a lot of times we think of mechanoreceptors, I wanted to make this statement, like just in our skin. Like we think, oh, like, okay, I'm exhibiting a force on my skin, so I can feel that I'm touching something or I'm interacting with something. But these mechanoreceptors are actually throughout our entire body. So, like, they're in our skin, they're in our organs, and in our muscles. For example, like when our intestine system is like getting food across, you can kind of feel like when certain foods, like even like fried chicken or something, is moving in certain parts of your intestines because you feel the stretching of the intestine. You're able to feel those visceral reflexes because of the mechanoreceptors that are all throughout your body. But because like the most prominent ones in the sense of touch is in the skin, we're just going to go over the skin mechanoreceptors. So, as a quick review, we have three main layers of our skin. Students know this, but we have our epidermis, and the epidermis is separated by the dermis, which is the middle layer of skin. The word epi means above or on top of, so just on top of. Dermis is the root for skin. So on the top skin, which is constantly replacing itself, is called the epidermis. That's our outermost layer. That's the one we come in contact with. The bottom of the epidermis has this layer of basal cells, which are called, what's this layer called, students? Oh, can you see this in the?
Yeah.
Okay. What is this layer called, students? The bottom layer, the base layer of the epidermis. Stratum basale is correct. So these basal cells, what they'll do is they'll mature and they'll go through a process of keratinization, and they'll actually get thinner as they grow because they're getting away from a blood supply source, so they're actually dying, and they become super thin and they become waterproof. And that's what we're interacting with here. And then they slough off, and this layer keeps replacing itself. So that's how our skin, our top layer of skin works. The middle layer, the dermis, that's what has the hair follicle. It has a lot of our receptors that we're going to be talking about today. It has like blood vessels. It has proteins. It has everything in there. The bottom layer is called the hypodermis. This has subcutaneous fat, has bigger blood vessels, and then like our musculature. So, two concepts we need to understand mechanoreceptors is first the receptive field. So, a receptive field means an area of skin that one neuron is responsible for covering. So let's say I have a neuron here that's like it's attached to a receptor, and I have one here, and they're all like, okay, I get this area of space, and they each have that area. But in other areas of our body, it could be like this entire space is covered by this neuron right here. So when I say small receptive field, I mean that one neuron covers a very small space. Like it could even be smaller than this. It could be like this small of space. And so this is the space that it covers or takes care of or senses from. A large receptive field then is the opposite. It's this example. of one neuron or sensory cell is taking care of a broad area of space. So that's what a receptive field is. So what would give a small or large receptive field be, or what would a small versus a large receptive field be good for, do you think? Like, why would we want in some areas to have neurons having small receptive fields and then in others have big?
I'm thinking like something like your lips would have the smaller because they feel
yes,
more,
totally
they're so sensitive.
That is a great like connection. So all of the areas that have small receptive fields have very detailed or sensitive sensory information.
Right.
So you brought up a perfect example. Our lips have a lot of neurons that have small receptive fields, so that they're very sensitive and it's finely detailed. Same as our fingertips, it's the same thing. The neurons in our fingertips have small receptive fields, as opposed to like our back, where it's like we don't really need to have fine detail, use the energy space. We can just have one neuron, I don't know, do like this whole section of our back and we're good. Great. Okay, so you actually already anticipated this. You got it right. It's the lips and fingertips have small receptive fields. But when I think about this, if you're having a hard time visualizing it, I kind of like think about like a garden versus like an orchard. So say if I was taking care of a garden, I can be a lot more specific and precise with what I plant and what I harvest. Or with an orchard, usually we pick one main thing of produce and then we can generalize it across the space. So something I want to bring up though, during our lab today, we're going to be doing something called 2-point discrimination. And this tests what type of field is happening in a certain area of your body, if it's a large or a small field. And what happens is you have this, like say if it's in a doctor's office and we're testing, hey, has there been damage to these neurons or something? We'll take a large circular thing and it has prongs spaced out at certain elements. And you'll touch someone with a prong, like on their finger, and you'll say, is that 1 point or 2 points? Like, is there two things touching you or one? And you know, this is one, so we touch it. Oh, it's one. But then, and you're not looking, your eyes are closed. Then you'll start having ones that are further and further apart from each other. And they're at certain distances. So say it's 2 millimeters, 3 millimeters, 4. Then they'll touch you, and I might still say 1, because if this falls within the same receptive field, then I can't really tell that it's 2 points or 1. So then the doctor will keep going up and see how much distance it takes for me to actually say, oh, it's 2 points now. So it's kind of interesting. So we're going to be doing that today. You guys can test which areas of your body have small or large receptive fields. Okay. So the other concept we need to understand with neurons and sensations in touch is slow adapting versus fast adapting. So this is just saying, how long does a receptor continue firing when there's a continual stimulus? So for slow adapting, what this means is that if a neuron or a fiber is slow adapting, it fires continuously, like it keeps sending signals to the brain when a stimulus is present. So, and this kind of works with like things we're holding. Like we always have a sensation that I'm holding something in my hand. That'd be from a slow adapting neuron. Like I'm always aware at all times. I don't ever not feel the stapler in my hand until I set it down. And the way I would kind of put this in different words is like the neuron is saying, I'm gonna keep telling you this is happening over and over. And I think of this like a little kid in the car when they're going on a trip, like a long trip, and they just keep asking like, are we there yet? Are we there yet? Are we there yet? And they're not gonna stop asking until you actually get there. That's exactly like the slow adapting fiber. It's gonna keep saying, hey, stapler's still in your hand, stapler's still in your hand, or like an alarm clock. Like it will not go off until you turn it off. That's the same thing with a slow adaptive fiber. Because we think of like adapting as like changing. So it's slow to change, it's slow to stop sending the signal. All right, quickly adapting though is the opposite. So in a quickly adapting fiber, it only fires or tells your brain when something has changed. So let's say, I don't know, let's say like this stapler all of a sudden got hot, started to heat up. started to heat up for some reason. Like maybe it's a automatic stapler and I had plugged it in so it starts heating up, or like a curling iron. My hand would sense that this is getting warm, but then at some point, our thermoreceptors are quick adapting. So I would just be generally aware, oh yeah, it started heating up, but it's not going to keep sending me that signal of like, oh, we're getting hot. It's like, no, we already know. We don't need to send it again. So that's the difference between quick and slow adapting fibers. I did this like a doorbell. Like, unless you're rude, you're not going to hold on to a doorbell. When you arrive somewhere, you're going to let them know, and that's all you need to do. All right. So with that knowledge, now we can actually understand the 4 main mechanoreceptors that are in our skin. So the first one we have is called Merkel discs or cells. This is for fine detail, edges, shapes, textures, just like Braille. So if you're blind and your Merkel cells don't work, you're screwed, because you wouldn't be able to discern those small bumps to then see the words that are on the page in Braille. The location of this is in the stratum basale. So we brought this up earlier. They're going to be around this layer right here. So they're very superficial in your skin, which makes sense, right? Like if they're super deep, how can they detect fine details? And these have small receptive fields. So like we say, they're very sensitive, they're detailed, and they're slow adapting. So when you touch something, it continually sends it to the brain. And like we said before, these have high density in our fingertips and our lips. And this is kind of like an example. If you were holding like a quarter in your hand, you could feel the difference between the front of the quarter and the back, because you could kind of feel the face on the front. It's the same thing. Can you think of an example in your life where you use your Merkel discs to feel or touch things, your day-to-day? Or just an example in general?
Shoot.
I know, it's hard.
Like, I'm thinking of things that I could touch. Like, I could touch sandpaper, or I could
Exactly. Okay, texture.
Yeah.
So say if you were like sanding something and you're like, oh, is this more coarse sandpaper or is it finer?
True.
You could use those. That's a great example. Sandpaper would be great. Like any texture. Or like if you're getting new clothes and you're like feeling the texture of something. Yeah. All right. Next up, our second one out of 4 is our Messner's corpuscle. Messner's corpuscle. This detects light touch or a fluttering sensation across our skin, or low frequency vibration. So not like our phone, but even lower frequency, like less strong. And this is like defined by me, just like a movement across your skin. Like when you feel a fly land on your head all of a sudden. Like, oh, I know it landed on me, and you like try to whack it off. That's detected by this. The location of this is the top of the dermis. So this is our epidermis, right? So it'd be right below that. And this will be the dermal layer, hypodermal layer. So it'll be right toward the top of the dermis. And this has a small receptive field as well, so it's detailed. Like we can feel the fly landing on our head, but it's rapidly adapting. So when a fly lands on us, we know it right at the beginning, but if we don't hit it off, you can kind of like remember like times in your life where then you look down and like, oh, it's still there. I didn't like hit it off. Yeah. And that's because it's rapidly adapting. It's not going to keep sending you that stimulus. Okay, third one. Ruffini endings. These are actually deeper now. So up toward the skin surface, we have the Merkel. We have the last one we talked about, but now we're talking about the Ruffini corpuscle, which is like toward the middle or the bottom of the dermis. I think I left this there, so ignore that. But this is skin stretch and sustained pressure. So some things we can think about with this is if you're sitting down in a chair and you like feel like you need to move because like you kind of get sore on one spot, that's because of this type of skin ending is telling you, hey, you've kind of been compressing this area too long. Move and shift in your seat. Or like an Indian rug burn. I was thinking that same thing. And this also has to do with, because of the stretch of like the different skin and muscles, it's very positional. So it has to do with grip, like holding on to the grip of a cup or something. Like if you feel it slipping out of your hand, you can catch it. Okay, last one. Finally, onto our last mechanoreceptor. This is dealing with, it's called the Pacinian corpuscle. This is the deepest one. It's kind of circular. And this detects high frequency vibration and deep pressure. So this would be like your phone buzzing in your pocket, It would be like if you're using a power drill and it's vibrating in your hand, or any type of just like someone touching you, because that's the deep pressure. Or if something fell on your leg and you're like, oh no, or like a weight fell on your foot, like this is what this would do. This is a large receptive field. The last one is as well, and it's fast adapting. So it tells you immediately when it's happening and then goes away. Okay, so those are our 4 major mechanoreceptors in our skin. So students, you'll want to know how to distinguish between these ones, because maybe on an exam, I could give you an example and you need to name which receptor is this circumstance, like your phone buzzing in your pocket. Okay, finally, the last 2, they're a lot more simple. The thermoreceptor is just our temperature receptor. And they don't have all these weird names of the people who discovered them. They just have cold receptors and warm receptors. Now, these receptors turn on at certain temperature gradients. So for the cold ones, it activates from 50 to 95 degrees Fahrenheit. Have you ever taken a ice bath?
Mm-hmm.
Did you take them often for your college?
Yes.
Okay, me too.
Yeah.
So after practice, I would take one after everyone because I feel like I recovered so fast.
Yes.
I have a question. So when you hopped in your ice bath, Ms. Dahlman, did you feel like there was a time domain where it was the worst?
Yes.
Okay, when?
We would, I want to say 45 seconds. We would grab something to read for 45 seconds.
Oh, that's interesting. So you would grab something to read to distract yourself.
ourselves.
Okay, that's really cool. Okay.
And it was like 40 something.
We're going to get to why that works later. But how long did you guys ice bath for?
I want to say 2 minutes. I don't know. I don't know if 2 minutes is when it didn't hurt anymore.
We did like 10 to 15 minutes.
Then maybe we did.
You probably.
Yeah, we did longer.
Yeah, you probably did like 10 minutes.
Maybe. Maybe it was 2 minutes when it stopped hurting.
I felt like it always stopped at 2 minutes.
Yeah, maybe that's why I'm thinking of 2.
Yes. So I used to ice bath every day, and it was always the first 2 minutes that were the worst.
Yeah.
I could go 30 minutes after those 2 minutes were up. This is because these receptors are partially adapting. So although you'll always feel the cold temperature, they will ease off as time goes because they don't want to keep sending the strength of signal. That's why ice baths get better after those first horrible 2 minutes. Yeah. And they're like, oh, I can manage this. So that's what's happening when we're taking an ice plunge or if we're in a sauna. You can see that this is 50 to 95 degrees Fahrenheit. The warm activate from 86 to 113 degrees Fahrenheit. There's some overlap in those 2 numbers. That's just an area where your body kind of feels neutral because both receptors would be turning on. And anything above this or below this would actually fall into the next category of receptor because your body's actually incurring damage. So what is the next receptor? Oh, I'm going to ask the class this because we're about to talk about nociceptors, which are the pain receptors. Do you think that it's good that our body detects pain? Everyone go around, everybody answer, and explain your answer. What do you think, Ms. Dahlman?
Yeah, because I think if not, you could kill yourself.
Yeah.
If you kept your hand on a hot stove and didn't know it.
And didn't know.
Right.
There's actually people that have this exact thing. So it's called CIP, congenital insensitivity to pain. It is so incredibly dangerous. We're almost done. Because the young children and people who have this, they literally can't feel pain. So many of them will actually bite their lips off or their fingernails. They can't tell if they have a fractured bone, so they'll keep walking on it until it pops out. And a lot of them will actually die from sepsis, which is like a bacteria infection of your blood, because they can't feel like bad. Like they don't feel bad. They don't feel like the inflammation. They don't feel like sore throat or anything. So they'll end up passing away because their body gets taken over by a bacteria, which is crazy. Yeah. So it's a big blessing that we have pain receptors. And this was just a quick question, but we're going to just go through it. The only place in our body that doesn't have pain receptors is actually in our brain. Our brain itself has no pain receptors. So that's just kind of crazy. All right, but keep going. Last 2 slides. So what the nociceptors do is essentially all they're doing is detecting tissue damage. So that's interesting. Our body sends a signal of pain when our body is in danger somehow. So if a cell is dying, if tissue is damaged or has trauma to it, our body will send up a signal to the brain, which is pain. And that's helpful for us as humans because then we want to get away from whatever's damaging us. So it responds to mechanical, thermal, and chemical damage. One of the main things that is cool is when a cell of our body is damaged, it'll release something called arachidonic acid. It's like a chemical that's released, like, oh no, we're in danger. This enzyme called COX will then take arachidonic acid and turn it into different things, one of them being prostaglandins. And prostaglandins is one of the things that is monitored by the nociceptors. So if nociceptors see that there's cell trauma, arachidonic acid, they're going to detect the prostaglandins and send pain signals up to the brain. This is, though, how NSAIDs work. So do you know any NSAIDs?
So like aspirin
ibuprofen.
Yeah.
Yes. Okay. If you take that, what it's doing is it's turning off the function of this enzyme so it can't turn it into a prostaglandin. So there's still the damage of the tissue, but there's no more prostaglandins to set off the pain receptors. Kind of interesting.
Yeah.
But lastly, there's 3 main fiber types in these pain receptors. 2 of them are for fast, sharp pain, and 1 is for slow, dull pain. So the A fibers are fast, sharp. The C fibers are for dull. I put up the neurons up here because the reason why the A fibers are fast is because they have myelinated axons. So students, you know why that would be, that it would be fast. It's because the signal will jump across the gaps between the myelin, and it's a much faster signal. So this is the difference between if I took a hammer, hit my finger, and I'd feel a sharp, fast pain, then it'd be gone, versus having like a tummy ache that is just continual, dull, lingering. But to conclude, there's something really interesting called the gate control theory. The idea is, hey, can we actually limit the pain that we're feeling? And the answer is yes. And the reason why is because pain travels on smaller nerve fibers up to our spinal cord and then up to our brain. But touch, pressure, and vibration are larger fibers that go to the same area in the spinal cord and then up to the brain. So if you ever like bang your arm on something and you rub it, you can feel like a decrease in the pain. Have you had that happen? Like, oh, you hit something and then you rub it. This is because when you activate the larger fibers that are like touch sensation, it'll mute the signaling from these smaller fibers. So it's actually bringing relief. This is why women who go into labor can use the TENS unit or the electrical stimulation units like on their back or on their belly. It'll decrease the sensation of the pain during contractions. And this exact thing is also the reason why you read something during the first bit of your ice bath, because they also have found that brain, mind, thought control can actually limit the smaller nerve fibers as well. So if you can distract yourself with music, meditation, or reading something, it will also control this gate that's opening up, letting the pain receptors signals through. So that's the end of today's lecture. Thank you so much to Ms. Dahman for taking her flex and being here.
Thank you.
And students, please have fun in our interactive lab today about touch and pain. See you guys. Yay!